Hey, welcome back everybody, and welcome to this first video for part 3.3, where we're going to look at image formation, and in this part by reflection. And so we'll be looking at mirrors. So this is the first time that we're going to talk about image formation by any means. So we're going to say something in general first about forming an image. Loosely speaking, there are three elements involved in forming an image: the object, the optical system, and then the image that's formed. Okay, so and I shouldn't say loosely speaking, I guess I should say generally speaking. So the idea is this: think of this as a flow chart. We're going to have some object. Now, usually these objects are what we call reflection objects. So there's going to be a light source somewhere, and light is going to be bouncing off of the object. So light goes from the source, hits the object, and light reflects off the object. Some of that light is going to be directed into what we call the optical system. It is possible to have what's called a transmission object. In that case, the light from the source would go through the object, but those are very special type objects. You might think of an old slide, if you've ever seen one of those carousel slide projectors. The light goes through there. Or a more modern version, the projectors that are used in classrooms, the ones that are mounted on the ceiling, or you might even have one at home, a projector. Light is passed through a LCD screen inside the projector, and then through a lens, and that forms the image. So those would be transmission objects where light's going through the object, but those are special cases. So most objects are reflection. So the light goes into the optical system. Now, the optical system is going to have what we call optical elements. These are things that change the path of the rays of the light. So these will be things like lenses, prisms, mirrors. You could have other things like you might have diffraction gratings in there, or some other diffracting aperture. Again, these are elements that change the path of the light. The light is then going to emerge from the optical system and form an image. Okay, so that's sort of a flow chart way to look at it. Now, it turns out when the light leaves the optical system, if you actually look at the light rays leaving the optical system, there are two possibilities you can have. Well, there's really three, but one would be a very special case that where the light rays coming out are all parallel. But I'll mention that in just a few minutes. But the two different ways that you can have the rays coming out are: you can have, as you see here, the rays are converging. So if you look at the optical rays after they've been bent by the optical elements in the system, the rays converge, which means they're getting closer together as you trace them from the optical system. In that case, you will get an image that's formed. It'll actually be formed at the converging point. We call that a real image. It's not the best name, but we call it real because there's actually light converging to points and forming the image. So if you would put a piece of paper at the converging point or a screen, you would see the image formed on that paper or screen. So we call that a real image. And the other possibility is the optical elements in the optical system actually end up diverging the rays. So as the optical rays leave the system, they are getting farther apart. Now, in that case, an image is still formed, but it is called a virtual image. And where the image is formed, this is a little strange. You'll see that we actually trace the diverging rays backwards. So we trace them straight backwards, and those diverging rays will appear to come from a common point. That would be the location of the virtual image. We call it virtual. It's a strange name. And that's because if you were to put a piece of paper at that apparent point where you trace the rays backwards, where they appear to meet, you wouldn't see the image on that piece of paper. Okay, the only way you can see this image is if you're looking at it with your naked eye, your eye would have to catch some of the diverging rays. So your eye would be over here on the right side, and it would be catching some of these rays. Some of these diverging rays would enter your pupil. What happens is that those rays will end up getting bent and refracted by the cornea and the lens in your eye, and those rays will actually converge onto your retina, okay, forming an image that you think, your brain thinks, is at that point where the diverging rays are traced back to. So you can see this virtual image as long as the diverging rays enter your eye. Or you could have another optical system like a camera lens. So if the camera lens catches some of these diverging rays, the camera can actually take a picture, a photo of the virtual image. Okay, so but that's the main difference between real image and virtual image. A real image is formed with converging rays that meet. A virtual image is formed with diverging rays, and the location of that virtual image, you're going to have to trace these rays backwards. Now, this is just a general description. Don't worry if you're not following all of it exactly, because I know it does sound a little confusing. We'll see examples of real image formation and virtual image formation with different optical systems and optical elements, and reinforce these ideas. I was going to say, just mention that the third thing that can happen is that you would have the rays coming out of the optical system neither converging or diverging, so they would be all parallel. And I mean, there actually is an application of that. There's something called a collimator, where you want to get light rays all parallel, get a nice collimated beam out, but you wouldn't be forming an image with that. Okay, so we're only looking here at image formation possibilities. Okay, so I wanted to just say some general things about forming images. Okay, now let's talk about specifics now, and what we're going to look at first in this video is what we call a plane mirror, or a flat mirror, but usually it's called a plane mirror. So this would be what you're looking in most probably in the bathroom in the morning. Okay, you're going to have a plane mirror there. Or maybe in your closet, right? You have a plane mirror mounted on your closet door, so it's flat. Okay, now the way this works, the way this forms an image, you can see it in this picture here. Over here, and there are some things that we're going to want to establish in terms of conventions that we're going to use over and over with this formation. So think of this blue dot right here as a point on the object. Okay, so this might be some extended object, but we're only looking at one point on it. Now, again, what happens is there's got to be some light bouncing off of this point on the object, and what we see is the path of some of those rays that have reflected off the object. So look, here comes one right here. See it right there? Now, what happens? Well, when it hits that reflecting surface, the light ray is going to get bent, so we're going to use what governs reflecting rays, and that's the law of reflection. So if this is your incident ray coming like that, by the law of reflection, it's going to get reflected this way, where the angle of reflection is equal to the angle of incidence. Okay, so that's what you see happening right here. This ray comes in, and it bounces or reflects this way. If I were to draw a surface normal for that ray, it would be a horizontal dashed line. It goes just like that. Okay. Now, I can do another ray. Here's just another arbitrary ray, and it also reflects according to the law of reflection, so it's going to go off like that. And similarly with this one. Okay. So in this picture, 3 rays are traced. It turns out, and we'll see this, I'll mention this again and again, you only have to actually trace 2 rays from an object point to figure out where the image point will be, and whether it's a real or virtual image. But 3's okay, but 2 would suffice. All right, now, what you do is after you've traced your 2 or 3 rays, you say, okay, look, are these rays diverging or converging as they leave the optical system? This is a really simple optical system. It has just one optical element, that single plane reflecting surface. So if you look at the rays that are leaving that surface, you can see that they're getting farther apart. They're diverging. That tells us that there's going to be a virtual image formed. Now, where is it? Look, trace these diverging rays straight back. So start over here on this one and trace it straight back. See that dashed line? Trace this diverging ray, this ray straight back. And this one. They all will appear to come from a common point, which is right here. That is the virtual image point. That is the location of the virtual image. Okay, you can see it labeled I there for image. Okay, and how do you actually see that image point? Well, it's shown in this little picture here, right? Some of these rays are going to have to enter this guy's eye. And now you're only seeing 3 of the rays here, right? You got to imagine there are a whole bunch, infinite number of rays, right, that are coming from this object point. So as long as and they're all going to be diverging, and they're all going to be traced back to this common point. So as long as some of those enter this guy's pupil, this guy, his brain's going to say the image is right here. Okay? If you think about it, when you look in the mirror in your bathroom, let's say, if you're brushing your teeth, if you ever look, you see your image, right, brushing your teeth, did you stop and ask yourself, where is that image? Where is it located? If I could reach out and touch it, where would I be reaching to? And I think if you stare long enough, right, you'll convince yourself, oh, I've got to reach like into the mirror, right? That image is behind the mirror. Yeah, it's a virtual image. If you try to reach out and touch it, of course, you're going to smash your hand into the mirror. Okay, but that's where the image is located. Now, you see labeled here 2 distances that are going to be important. They're labeled P and Q, which is a common convention. This is known as the object distance, P. It's the distance from the object to the optical element, in this case, that surface, the flat surface of that plane mirror. So that's the object distance. And then the distance from that optical element to the image location, labeled Q here, that's known as the image distance. Okay, and we'll see those again and again pop up. Whoops, I didn't want to do that. Oh, yes, I did. I'm sorry. The reason I want to do this is this shows the exact same image being formed, but this is what I would call an official ray trace. And we're going to do these for lenses. When we get to lenses, we'll be doing ray traces a lot, and you have to know how to do a ray trace. So you should also know how to do the official ray trace for a plane mirror. So when we do an official ray trace, the first thing we do is we draw this horizontal line down here. That's known as the optic axis. That's a reference axis. The next thing we do is we're going to draw our optical element. So our optical element is just a plane mirror, so we can just draw this vertical straight black line. Okay, we don't even need this little shaded part here, just that straight black line there. That represents the reflecting surface of the mirror. The next thing we do is we draw a generic object, and the generic objects are always going to be arrows. So we would draw just what I would call an upright arrow pointing up from the optic axis, right, up to here, just some arbitrary height. Okay, so we draw that blue arrow. Now the next thing we would do is we would start doing the ray tracing. So when we do our official ray trace, we're always going to image the tip of the object arrow. So the tip of the object arrow is our point of interest. And we're going to draw 2 rays from it. The first ray will always be parallel to the optic axis. So you see this ray right here, like that. Okay, just this ray pointing to the right. We'll always draw that, no matter what the optical element is. Now, then you figure out what happens to that ray. Well, this is a reflecting surface. If this ray comes in like this from the left, traveling to the right, it's going to reflect, and it's going to reflect right back on top of itself, right back to the left, because the angle of incidence is 0. The surface normal for that ray would be a horizontal line. So the angle of incidence is 0, so the angle of reflection is 0. So this first ray, it goes to the right and it reflects right back on top of itself to the left. So we've completed one ray. Okay, now the other ray that we're always going to draw, no matter what the optical element is from the tip of the object arrow. It's going to be a ray that comes down and hits the intersection point of the optical element with the optical axis. Okay, so that's the intersection point right there. So we draw this ray. Then we're going to follow that ray using either reflection or refraction laws. Well, in this case, again, it's a mirror, so we use the law of reflection. So this ray is going to reflect down to the left like that. And by the law of reflection, this is the angle of incidence, theta. That's got to equal this angle of reflection, that angle, theta. Because for this ray that's coming down like this, slanting down like this, the surface normal is, in fact, the optic axis. Okay, so look, we've completed the tracing of the rays. The first ray we know goes right back to the left horizontally. The second ray comes down and then goes down slanted to the left like that. So once we're done tracing the rays, we ask ourselves, do these rays converge or diverge? And they diverge. As they leave the optical system, this one's going to the left horizontally, this one's going down to the left. They're getting farther apart. That tells us we have a virtual image. So where is it? So what we do is we trace those two rays backwards. All right, so here's that ray going to the left, right? It's reflected going to the left. So trace it back. And this ray that leaves the optical system, it's going down to the left. So trace it backwards with this dashed line. And those two dashed lines should meet. And where they meet is the tip of the image arrow. Boom, right there. So then once you know where the tip of the image arrow is, you can just quickly draw it in down to the optic axis. Right? And we draw that yellow arrow. We did it. We found out where the image is. Okay, now, some important distances and heights. I've already mentioned the object height, the object distance, P. That would be from the tip of the object arrow to the optical element. The image distance is from the optical element to the image arrow. That would be Q. And then two heights we're going to introduce. The object height, that's measured from the optic axis to the tip of the object arrow. So that would be H in this picture. And then the image height is from the optic axis to the tip of the image arrow. And that is H prime. That's usually called H prime. Okay? So there's the official ray trace. Now, to describe this image, we would say it's virtual, right? Formed with diverging rays. We would also call this upright, or you might hear non-inverted or not inverted. In other words, it's not flipped. It's not inverted with respect to the object. So commonly that's called an upright image. It's not inverted. And then we can introduce in this slide a new physical quantity that we call the lateral magnification, big M. And that would be defined simply, which means it's a simple formula, it's not a complicated one, as image height over object height, H prime over H. And for a plane mirror, H prime will equal H, so you'll always get a lateral magnification of 1. Okay? So that's what I want to introduce there for the plane mirror. Okay, and again, next time you're brushing your teeth, sort of look at that image and you might be able to convince yourself, yeah, it's the same height as the object. In fact, as you walk away from the bathroom mirror, as you step back from the mirror, you should see your image also stepping back. Okay? So the image distance is always equal to the object distance, it turns out. These distances, P and Q, are the same, as are these two heights. Okay, I think that's all I want to say about that. Oh, no, it's not. I want to go over one application of a plane mirror, and that's your car's rear view mirror. this is a nice application using reflection. You guys might know that there's a daytime setting and a nighttime setting for your rear view mirror in your car. So at night, particularly when there are cars behind you with those really bright headlights, there is a setting where you can reduce the intensity, the brightness of those lights. And the way it works is it's a really simple solution. Your rear view mirror has this sort of metallized reflecting surface, but in front of that, there's this wedge of glass. Okay, this wedge of glass. So it's not a straight piece of glass that's parallel to the reflecting surface. It has this wedge shape. So the way it works is like this. Look at the light coming over your shoulder. Look at this ray right here. Because at nighttime, those bright headlights, that light's going to be coming over your shoulder. So so focus on that. When that ray hits that piece of glass right there, by the law of reflection, you're going to get light reflecting down this way, down that way. Now, not a lot of light energy reflects off of that glass surface. Okay, not a lot. Some does, but not a lot. The majority of the light is going to be refracted into the glass, reflect off that back metallized mirror reflecting surface, come back out, and then refract away from the surface normal and enter your eye. So at its daytime setting, a lot of the light, right, that's coming over your shoulder is going to enter your eye. That's fine, right, because it's not going to be super bright light coming over your shoulder. That's what you want. Okay, but at nighttime, right, if that main source of light, the headlights behind you, if coming over your shoulder, what's going to happen is a lot of, if not, well, not all, but almost all of that light energy from the headlights is going to enter your eye. And you're going to say, ouch, ooh, my pupils are already dilated because it's nighttime and now I have all that light coming in, right? So those car headlights behind you are just too bright. So what you do is you just flip your mirror and you get the nighttime setting. You end up flipping your mirror up like this, and look at what happens now. So you have the bright headlight energy coming straight across your shoulder, right? So a little bit of the energy reflects off of the glass surface now into your eye. That's okay that it's only a little bit, because the headlights are really bright. So just a little bit of that energy gets into your eye. You're okay, you can see it. The majority of the light actually gets transmitted and refracts into the glass, bounces off that reflector, comes out and gets refracted away from the surface normal. It actually gets refracted and sent up to the ceiling in your car, up to the roof. So the majority of the light, of the headlamp energy, is getting refracted up onto your roof. Only a little bit gets reflected into your eye. That's great. You can see that there are headlights behind you. You know there's a car behind you, but right, it's not blinding you with the headlight. Okay, I thought I'd just talk about that. Ooh, I've talked long enough in this video. I'll see you in the next video where we start talking about curved mirrors. Yep. Okay, bye-bye.